Welcome to Grandpa's Late Nights. It's good to have you here again. Pull the blanket up a little higher, settle your head into the pillow just the way you like it, and let your shoulders come down from wherever they've been holding all day. There's no hurry tonight. There's nowhere either of us has to be. The porch light's on, the kettle's gone quiet, and we've got all the time in the world to talk about something soft and strange and very, very old. Now, here's a curious little thing to know before you drift off. Right now, in this very room, wherever you happen to be, in your bed, on the couch, on a long train ride home, maybe with one lamp still glowing in the corner, there is light passing through you. Not the light from your lamp, not the light from your screen. Older light than that, much, much older. The oldest light there is, in fact. It has been traveling for 13.8 billion years to get here, and a faint trace of it is moving through the air around you this very moment, through the walls, through the blanket, through you, gently and without a sound. And it's cold now. So cold. This light has been falling and stretching for so long that it has cooled to less than 3 degrees above the coldest temperature anything can ever be. 2.725 degrees above absolute zero, to put a number on it, which is colder than the deepest, darkest corner of empty space you could ever imagine. A whisper of warmth that's almost no warmth at all. And it's everywhere. It's coming from every direction at once, all the time, washing through the room like the faintest tide. You can't feel it. You'll never feel it. But it's there, the very first glow the universe ever let loose, and tonight it's keeping you company whether you knew it or not. That's the kind of thing we're going to sit with tonight. The kind of thing that's enormous and ancient, and yet, somehow, when you say it quietly in the dark, becomes gentle, almost cozy, a reason to feel small in the nicest possible way. Now, before we go any further, and I'll keep this short, because the last thing I want is to clatter around and wake you up. If you find these slow, late-night wanderings help you drift off, a quiet like and a subscribe really do help keep this little porch light burning. I'm just one old fella with a microphone and too many things rattling around in his head, and small channels like this one really do lean on your help to keep going. So if you've got a free thumb before your eyes close, that means more than you know. And to those of you who've already subscribed and keep coming back, night after night, thank you. Truly. I think about you out there more than you'd guess. And while you're settling, I'd love to know, where in the world are you listening from tonight? What time is it in your corner of things? Leave it down below if you feel like it, even just a town and a time. I read them. It's a small comfort on my end, knowing roughly where all these scattered, sleepy souls are tucked in. So tell me, I'll be wondering. There. That's the housekeeping done. Now we can take our time. Here's the thing I want you to know first, and it's the most important thing, so let me say it slowly. You don't have to follow all of this. You really don't. If your eyes close in the next 5 minutes, and you never hear the end, that's not a failure. That's the whole point. That's a job well done as far as I'm concerned. The ideas will still be here tomorrow. The universe isn't going anywhere. It's been patient for 13 billion years. It can wait for you to wake up. So there's no need to concentrate, no need to remember any of these names or numbers, no test in the morning. Just let the words roll over you like water over smooth stones. If you catch one and it interests you, lovely. If you let it slip by, that's lovely too. We're going to move slowly tonight, slowly and softly, one idea at a time, and I'll hold your hand the whole way through. I'll try, as I always do, not to make any of this so interesting that it keeps you awake. Though I'll admit I'm not always good at that, but if it does keep you up a little, well, at least you'll have learned something for your trouble. A fair trade, I'd say. So, let's talk about a number. You've probably heard it. The universe is 13.8 billion years old. It gets said all the time, doesn't it, in that flat, confident way, as if someone simply walked up and read it off a label on the side of the cosmos. 13.8 billion. And most of the time, when you hear that number, that's where the conversation stops. There it is. Move along. Nobody ever seems to tell you the part that actually matters, which is the part I think you'll find the most comforting of all when you really sit with it. Because here's the question. Nobody asks the one I want to gently answer for you tonight. How could anyone possibly know that? Think about it. There was no one there to see it begin. No witnesses, no old photographs, no diary, no clock running in the corner with a dusty little second hand, ticking away since the dawn of everything. The universe didn't leave us a birth certificate. So how on earth, or rather, how off the earth, could anyone say with a straight face that it's 13.8 billion years old and mean it? That's a fair thing to wonder. It's the most natural thing in the world to wonder. And the honest answer is the loveliest part of the whole story. The answer is that we didn't measure it just once, with one clever trick that you'd have to take on faith. We measured it 3 completely different ways, 3 separate roads to the same place, built by different people in different decades, using physics that has almost nothing in common from one road to the next. 3 clocks, if you like. 3 entirely different kinds of clock, ticking in 3 entirely different ways, that have no reason whatsoever to agree with each other. And yet they do. That's the thing. That's the whole quiet miracle of it. And it's what I want to leave you with by the end of the night, even if you only catch the first 10 minutes of it. 3 clocks that share no parts, no maker, no shared way of telling time, all pointing at very nearly the same number. About 13.8 billion years. And when 3 strangers who never compared notes all give you the same answer, well, you start to believe them. Not because any one of them is so persuasive on their own, but because they agree. The agreement is the thing you can lean on. The agreement is what lets you rest easy. Let me give you a feel for just how different these 3 roads are, so you can appreciate later how strange it is that they meet. The first clock is built out of stars, the oldest stars we can find, ancient, faded things burning low out at the edges of our galaxy. We read their age the way you might guess the age of an old tree, and that age tells us, at the very least, how old the universe has to be. Because you see, the universe can't be younger than the things inside it. That much is simple. It's a kind of flaw underneath the whole question. The second clock is built out of motion. The galaxies, all of them, are drifting apart from one another, the way specks in a slowly stirred pot drift away as the water spreads. And if everything is drifting apart now, then long ago it must have been closer together. So we do something rather wonderful. We run the film backward in our minds and in our mathematics, watching everything slide back toward a single moment when it was all gathered up in one place. And we ask, how long ago was that? That gives us a number 2. The third clock is that ancient light I told you about at the start. The cold whisper passing through your room right now. It carries within it, hidden in its faint, even glow, a record of how old it is and how far it's come. We can read that record. And it gives us a number too. 3 roads, stars, motion, light. 3 kinds of physics that have truly almost nothing to do with one another. The way a star burns through its fuel has nothing to do with the way galaxies fly apart. The way galaxies fly apart has nothing to do with the temperature of the oldest light in the sky. They're separate worlds, these 3. And if any one of them were badly wrong, if the star clock were off, or the motion clock were broken, or the light clock were misread, there'd be no reason at all for it to land near the other 2. It would just give some random answer of its own, off in the wrong direction, and the disagreement would shout at us that something was the matter. But that's not what happens. What happens is they all come home to roughly the same place, about 13 billion years from the stars, somewhere near 13.5 to 14 from the motion. And from the light, the most precise of the three, 13.787 billion, they overlap. They land gently in the same quiet spot. And that, my friend, is why we trust the number, not faith. Not one clever person insisting. Just three honest strangers agreeing. Now let me say a little more about that very precise figure, because I think there's something soothing in it too, once you understand what kind of thing it really is. 13.787 billion years. That's the best number we have, and it comes from the third clock, the one made of ancient light. And here's the part that always quiets my mind a little. The uncertainty on that number, the little give or take that any honest measurement carries, is only about 20 million years. Now, 20 million years sounds like a lot, and on a human scale, of course, it's almost beyond imagining. But set it against 13.8 billion, and it's a whisper. It's about 15/100ths of 1%. Imagine measuring something the length of your whole life and being unsure only of a single afternoon. That's the kind of precision we're talking about. For the age of absolutely everything, it's a remarkable thing that we can be that sure about something that old and that vast. But, and here's where I want to be honest with you, because I think honesty is the most relaxing thing of all when you're trying to fall asleep. That number is not something anyone read off a dial. Nobody held up a ruler to the cosmos. There is no instrument anywhere that measures the age of the universe directly. Not one. That's worth understanding because it changes how you should feel about the number, and I think it makes it more trustworthy, not less. What we have instead is a model, a picture of how the universe is put together and how it behaves over time. The best picture we've managed to build, refined over many decades by a great many patient people. It has a rather plain name. They call it the Lambda CDM model. Don't worry about the letters. I'll explain what's inside it later, gently, when we get to the third clock. For now, just think of it as our best working sketch of the cosmos. What it's made of, how fast it's spreading out, how its motion has changed over the ages. And the age of the universe is something that falls out of that sketch once you fit it carefully against everything we actually see in the sky. So it's a derived number, an inferred number. We feed in the things we can genuinely observe, the temperature of that ancient light, the pattern of its faint ripples, the speed of the drifting galaxies. And the model hands us back, among other things, an age. 13.787 billion years. It's a conclusion, not a reading. And I find that comforting, not unsettling, because it means the number isn't resting on one fragile measurement that could be knocked over. It's resting on the whole structure, the whole agreeing picture, all those independent roads woven together. You'd have to knock down a great deal, all at once, in just the right way to move it. So that's where we're headed tonight. 3 clocks, stars, motion, and light. We're going to walk down each road slowly, one at a time, in no hurry at all, and I'll show you how each one is built and how each one arrives on its own at very nearly the same answer. And then, right at the end, when all 3 have come home, I'll show you the thing I find most beautiful of all, which is that they weren't always in agreement. There was a time, not so very long ago, when the clocks fought with each other, when one of them seemed to say something impossible, and the way that quarrel was resolved is itself the best reason of all to trust where they finally settled. But that's for later, no rush. Let's begin with the stars. And let me open with a little puzzle, a thread I'll leave hanging just over your head for a while, the way you might leave a window cracked on a warm night. There is a star, a real particular star, with a real name and a real address in the sky. It sits in the constellation Libra, the scales, the balance, that quiet little pattern of stars you might find on a clear night if someone showed you where to look. And this star, when astronomers first measured it carefully, gave them quite a fright, because the number that came back said it was about 14.5 billion years old. Now stop and feel that for a moment slowly in the dark. 14.5 billion. But we've just spent all this time saying the whole universe is only about 13.8 billion years old. So here is a star, an old, faint, particular star you could point a telescope at tonight, that appeared, when they measured it, to be older than the universe that contains it.
That can't be right, can it? A child older than its mother, a tree older than the forest it stands in. It's the kind of thing that if you saw it written down, would make you certain someone had made a mistake somewhere. And the astronomers thought so too. They gave the star a nickname, a rather affectionate one, given the trouble it caused them. They called it the Methuselah star, after the old fellow in the ancient stories who was said to have lived nearly 1,000 years.
The oldest of the old, a star that seemed to have been around since before there was anywhere for it to be. How can a thing be older than everything? That's the puzzle, and I want you to hold on to it loosely, the way you'd hold a warm mug you're too sleepy to drink from. Don't try to solve it. Just let it sit there glowing faintly in the back of your mind, because the answer is genuinely lovely, and it tells us something important about how this whole careful business of measuring the cosmos actually works. There's a catch in that number, 14.5 billion, a small, honest catch that makes all the difference. And when we get there, slowly, in good time, you'll see that the star and the universe make their peace after all, and that the way they make their peace is one of the gentlest lessons in all of this. But to understand the catch, we first have to understand the clock itself. We have to understand how anyone could look at a faint old star and say anything at all about its age. Because it isn't obvious, is it? You can't ask a star how old it is. It won't tell you. It just sits there, burning the way it has for an unthinkable span of time, long before there was anyone to look up and wonder, and yet we can read it. We've learned to read the ages of stars the way you might read the age of a candle by how far it's burned down, and the very oldest ones we can find, out at the lonely edges of our galaxy, all tell us the same patient thing, that they have been burning for something close to 13 billion years, which means the universe that made them, the universe that gave them somewhere to burn, must be at least that old. That's our first clock. That's our floor, the solid ground beneath the whole question. So let me show you slowly where the oldest stars live and how we learn to read their long, quiet lives. Let me take you out to the edge of the galaxy, to those great gathered swarms of ancient suns, and we'll begin to learn the trick of telling time by starlight. Settle in a little deeper now. We're going somewhere very old and very far and very calm. They're called globular clusters, and they are some of the loveliest things in the sky. Picture, if you can, a great ball of stars, not a few dozen, not a few thousand, but hundreds of thousands of them, sometimes millions, all bound together by their own gravity into a tight, glowing sphere. They orbit our galaxy from the outside, way up in what we call the halo, far above the flat spinning disk where you and I and the sun all live. They're like little cities of light, hanging in the dark, keeping their own time. And the wonderful thing about them, the thing that makes them so useful to us tonight, is that all the stars in one of these clusters were born together. At roughly the same moment, out of the same great cloud of gas, the whole family lit up at once, brothers and sisters, all the same age. That matters more than it might sound, because it means that when we look at a globular cluster, we're not looking at a random scattering of stars of every different age all jumbled up. We're looking at a single class of children photographed together, all having lived exactly as long as one another. And once you know that, you can start to do something rather beautiful with them. Here's the idea. Stars don't all burn the same way. A big, heavy star burns hot and fast and furious. It throws its whole fortune of fuel onto the fire at once, blazes blue, white and brilliant, and burns out quickly in just a few million years sometimes. A small, modest star is far more careful. It sips its fuel, glows a gentle red, and can keep going for tens of billions of years, longer than the universe has so far existed. So in any family of stars all born together, the big spendthrift ones die first, while the small, thrifty ones are barely getting started. And that quietly is a clock. Because as the cluster ages, you can watch the dying creep down the line. First, the very biggest stars burn out. Then, as more time passes, the next biggest, then the next. It's as if you lit a long row of candles of different thicknesses all at the same moment. The fattest ones gutter out first, and by looking at exactly how far down the row the burning out has reached, you could tell how long ago they were all lit. The stars do the same. The point in the family where stars are just now, today, beginning to run out of fuel and change, astronomers call that the main sequence turnoff. And where that turnoff falls tells you the age of the whole cluster. I love that phrase, the turnoff. As if these stars have been driving along a long, straight road together for billions of years, and at a certain point, one by one, in order of size, they signal and turn off it, leaving the highway of their youth behind. The bigger the star, the sooner it takes the exit. So you look for the largest stars that are still on the road, still steadily burning, and the ones just beginning to leave. And from exactly where that happens, you read the time. To see this, astronomers make a kind of map. It's one of the oldest and most useful pictures in all of astronomy, and it has a wonderful, slightly clattering name, the Hertzsprung-Russell diagram, named for the two men who first drew it. Don't worry about the name. Think of it simply as a chart, where you plot every star in the cluster by two things: how bright it truly is, and what color it shines. And when you do that for a whole globular cluster, the stars don't scatter randomly across the page. They fall into a clear, curving shape, a long diagonal band with a little hook bending off it at one end. That hook, that turning point, is the turnoff. And the lower down it sits, the older the cluster, the whole age of hundreds of thousands of ancient suns read off the bend in a line on a chart. There's something almost unbearably peaceful about that, isn't there? All that fire and time gathered into a single quiet curve. And when astronomers do this, when they find the oldest of these clusters and read their turnoffs, the answers come back remarkably consistent. The very oldest globular clusters land somewhere around 12 to 13 billion years. There's one called NGC 6397, a tight little swarm down in the southern sky, that comes in near 13 billion.
And another, a famous one called M92 up in the northern constellation of Hercules, that's reckoned just as old. Different clusters in different corners of the sky, measured by different astronomers, and they keep agreeing. Around 13 billion years, the first faint outline of our number, drawn entirely in starlight, with no mention yet of any expanding universe, any distant glow, any of the other roads we'll travel later. Just stars and the patient arithmetic of how they burn.
Now you might be wondering, and it's a fair thing to wonder drifting there in the dark, whether there's any way to check that. Whether reading a bend in a line is really enough to trust. And here is one of the quietly reassuring things about this whole subject, the thing I most want you to carry off to sleep. The stars give us more than one way to check. They keep a second clock entirely of a completely different kind, and it tells almost exactly the same time. This second stellar clock is made of dying embers. When a star like our own sun finally runs out of fuel, long, long from now, it doesn't explode. It simply lets go of its outer layers in a soft, glowing sigh, and what's left behind is the bare, hot core, a white dwarf, we call it, a dead star, no bigger than the Earth, but unimaginably dense, holding the mass of a sun in a ball the size of a planet. And here's the gentle part. A white dwarf doesn't burn anymore. It has nothing left to burn. All it can do is what an ember does when you take it off the fire. Slowly, steadily, predictably, cool down, fade, dim, drain its last warmth out into the cold of space over billions of years. And because they cool at a pace we understand, white dwarfs become little timers. The hottest, brightest white dwarfs are the ones that have only recently died. The faintest, coolest, most barely there ones are the oldest, the ones that have been fading the longest. So if you go into one of those ancient globular clusters and hunt down the very dimmest, coolest white dwarfs you can possibly find, the ones that have nearly disappeared into the dark, you've found the longest cooling embers in the place. And you can ask how long it would take an ember to cool that far. The answer, once again, comes back near 12 to 13 billion years. Think about what's just happened there. We measured the age of these old star cities one way, by watching where the living stars begin to die, the turn-off. And then we measured it a completely different way, by timing how far the dead stars have cooled. One method looks at the stars that are still burning. The other looks at the cinders of stars that burned out long ago. They have almost nothing in common, and yet they agree. Both of them quietly, independently, settle on 13 billion years or so. When two such different methods nod at the same answer, you start to feel the ground go firm beneath you. Not because anyone insisted, but because the universe keeps telling you the same thing in different voices. There is even a third way the stars keep time, and it's perhaps the strangest and most poetic of all. Some very old stars carry within them faint traces of radioactive elements, heavy things like thorium and uranium, the very same kinds of atoms we find in the rocks beneath our feet. And radioactive atoms have a peculiar, beautiful habit. They decay. They slowly, reliably, unstoppably turn into other things at a rate so steady you could set the cosmos by it. It's the same principle that lets us date ancient bones and old wood here on Earth, only stretched to an enormous scale using atoms whose clocks tick, not in thousands of years, but in billions. By measuring how much of these radioactive elements is left inside the oldest stars and how much has already decayed away, we can ask how long the decaying has been going on, how long these atoms have been quietly ticking down. And the answer, you can probably guess by now, comes back somewhere around 13 to 14 billion years. 3 different stellar clocks, the turn-off, the cooling embers, and the radioactive ticking, all 3 in their own languages telling the same long story. So that is our floor. That is the solid ground I promised you. The oldest stars we can find, measured 3 separate ways, all say the same patient thing, that they have been here for something close to 13 billion years, and a universe cannot, of course, be younger than the things living inside it. A house cannot be newer than the furniture standing in its rooms. If there are stars this old, the cosmos that cradles them must be at least as old, and very likely a little older still, old enough to have made them in the first place. The stars set a minimum, a line in the sand of time below which the true age cannot fall. Which brings us gently back to that one strange star I mentioned a while ago. The one in Libra, the one that, for a little while, seemed to break the rule entirely, that seemed, impossibly, to be older than the very universe that made it, because if the oldest stars set the floor, what on earth do you do with a star that appears to sink straight through the floor and out the other side? Let me tell you about that star now, slowly, the way it deserves. Let me tell you about Methuselah. The name itself carries weight, doesn't it? Methuselah. In the oldest of old stories, Methuselah was a man said to have lived 969 years, the oldest human being in the biblical record, a figure so ancient he became a kind of shorthand for age itself. When astronomers gave that name to a star, they were making a very deliberate choice. They were saying, this one is old, this one is very, very old. The star's official designation is HD 283, just a catalogue number, dry and administrative, like a file number on a very old document. But the name Methuselah suits it better. It sits in the constellation Libra, not far from the horizon in the evening sky, depending on where you are in the world and what time of year it is. It is not a dramatic star. You wouldn't look up and feel anything particular if nobody told you what you were looking at. But once you know, it's hard not to feel a little strange standing under it. For a while, in the early years of this century, the numbers around HD 140283 were genuinely troubling to the people who study such things. Not in a crisis sort of way. Scientists are generally calm people, or at least they work very hard to appear calm, but in the way that a piece of furniture simply does not fit through the door, no matter which way you tilt it. The measurements kept suggesting that this single star, this one quiet object in Libra, was somewhere around 14 to 15 billion years old. And the universe, according to our best estimates at the time, was about 13.8 billion years old. You see the problem. A thing cannot be older than the thing that made it. A candle cannot be older than the factory where it was poured. A river cannot be older than the mountains it carved through, and a star, assembled from hydrogen and helium in the churning early cosmos, cannot be older than the cosmos itself. And yet, there it was. The measurements kept coming back wrong, or rather, the measurements kept coming back in a way that told a story that could not quite be true. The resolution, when it came, is actually one of the more reassuring small stories in modern astronomy. Not because it involved some dramatic reversal, some announcement that everything we knew was wrong. Quite the opposite. The resolution was quiet and methodical and showed exactly how science is supposed to work when the numbers are stubbornly uncooperative. But to understand the resolution, you first have to understand how the age of HD 140283 was measured in the first place. And that takes us back to the Hubble Space Telescope. In 2013, a team led by an astronomer named Howard Bond et al., as the papers always put it, the et al. Covering the careful work of many hands, used the Hubble Space Telescope to make a very precise measurement of the star's parallax. Parallax is one of the oldest tricks in the astronomer's book, and it is wonderfully simple in principle, even if the execution requires extraordinary precision. Hold one finger up in front of your face. Close your left eye. Now close your right eye instead. Your finger appears to jump. It has not moved, of course. What has moved is your point of view. The background behind your finger is fixed, and the shift in apparent position tells you through simple geometry how far away your finger is. Astronomers do exactly the same thing with stars. As the Earth orbits the Sun, our point of view shifts across a diameter of about 300 million kilometers over the course of a year. Nearby stars appear to shift slightly against the fixed background of more distant stars. The size of that shift, with the parallax angle, gives you the distance with remarkable precision. For a nearby star like HD 140283, a relatively close neighbor, at about 190 light-years away, the Hubble Space Telescope could pin down this shift to a tiny fraction of an arcsecond. An arcsecond is a 60th of a degree. We are talking about precision that makes your head swim a little if you think about it too carefully, and knowing the distance is everything. Because once you know how far away a star is, you can work out how intrinsically bright it is, how much light it is actually producing, rather than how much light happens to reach our eyes. A dim candle close up looks brighter than a blazing bonfire far away. Distance is the great confuser of brightness, and parallax is the tool that cuts through the confusion. With the distance pinned down by Bond and his colleagues, the team could determine HD 14283's true luminosity, its temperature, and its chemical composition with much higher precision than had been possible before. And from those three things, luminosity, temperature, composition, you can work backward through the known physics of stellar evolution and ask, how long would a star like this need to burn to reach this state? The answer came back as approximately 14.5 billion years, with an uncertainty of about plus or minus 800 million years. That last part is critical, plus or minus 800 million years. The measurement was not a razor-sharp number, it was a range, and here is where the resolution lives, quietly and patiently, waiting to be seen. Think of it like this. Suppose someone hands you a sealed box and tells you there is an object inside between 12 and 14 centimeters long, and you have a shelf that is between 13.5 and 14.5 centimeters wide. Will the object fit on the shelf? You cannot say for certain. The ranges overlap. There is a real possibility that it fits, and a real possibility that it doesn't, and you will not know until you open the box and take a more careful measurement. That does not mean the object is too long. It means your measurements are not yet precise enough to say. HD 140283 was the box. The shelf was the age of the universe. The initial measurement, with its error bars of 800 million years, meant that the star's true age could be anywhere between roughly 13.7 and 15.3 billion years. The universe's age, at 13.8 billion years, sits comfortably inside that range. The star might be older than the universe, or it might not, and the measurement, as precise as it was, simply could not yet distinguish between those two possibilities. And as measurements have been refined since 2013, the central estimate for HD 140283 has crept downward. More careful analyses of the star's helium content and the precise modeling of its internal structure have suggested its age is probably closer to 13.5 to 14 billion years. Still ancient, still extraordinary, but almost certainly younger than the cosmos itself. The apparent paradox has not disappeared entirely. There is still a small sliver of uncertainty, but the contradiction that once seemed so stark has softened considerably. The star and the universe are not at war. They are, within the margins of what we can currently measure, consistent. The furniture fits through the door, once you measure it more carefully. This is not a failure of science. It is exactly how science works. You make a measurement. The measurement has uncertainty. You report the uncertainty honestly. You refine the measurement. The picture sharpens. The contradiction resolves. Quietly, methodically, over years and decades, the numbers converge. Numbers. HD 140283 is still remarkable, one of the oldest known stars forged in the very first generation of star formation, a survivor from an era so early that the universe contained almost nothing but hydrogen and helium, when no planets existed anywhere, when the concept of life was not even a distant possibility, in a cosmos still barely organized enough to form a galaxy. It is remarkable not because it broke the rules, but because it walked right up to the edge of them and then, on closer inspection, respected them after all. And it points us, as all the stellar clocks do, toward that same wide neighborhood on the timeline, 13 to 14 billion years. The Methuselah star, the globular clusters with their main sequence turn-offs, the cooling white dwarfs, the radioactive thorium and uranium quietly ticking in the cores of ancient suns. All of them, in their different languages, say the same thing. Something very old is going on, something that has been going on for a time almost too large to hold in the mind. So there you have it, the floor, the solid lower bound set by the oldest stars we know, the stellar clock, independent of any telescope satellite, independent of any measurement of the expansion of space, independent of any physics having to do with the early universe's glow. Just the straightforward, patient reckoning of how stars age. And that clock says at least 13 billion years, probably a bit more. Now, if you are still with me, and if you have drifted off somewhere along the way, that is perfectly fine. The stars will be here whenever you come back. There is a second clock we have not yet looked at. A clock of an entirely different kind. One built not from starlight, but from motion, from the slow, vast, unstoppable spreading of space itself. Imagine for a moment that you could film the entire universe, every galaxy, every cluster of galaxies, the whole enormous structure of it, and then imagine playing that film in reverse, running it backward. The galaxies, which are currently flying away from each other in all directions, would begin to slide back toward one another. The great voids between them would shrink. The filaments and walls of the cosmic web, those vast structures where galaxies gather like dew on a spider's web, would pull together. And if you kept running the film backward, farther and farther back in time, everything would compress and compress and compress, drawing inward until all of it, all the matter, all the energy, everything that would one day become every star and planet and person and thought, was packed together into an almost incomprehensibly small and hot and dense state. And there would be a moment, at the very beginning of that reversed film, when the whole thing would be touching, when it all began. The question is, when was that moment? How long ago does the film have to run? To answer that, you need to know how fast the galaxies are currently flying apart. And that is what the second great cosmic clock measures, the expansion rate, the speed at which the universe is spreading, the number that carries the name of the man who first measured it, though as we shall see in a moment, that name is only partly accurate. The number is called the Hubble constant, and the story of how we came to know it begins, as so many stories in 20th century astronomy do, not with the person whose name ended up on the discovery, but with someone whose name very nearly didn't. Her name was Henrietta Swan Leavitt, and she worked at the Harvard College Observatory in the early years of the 20th century, in a time and a place where the most patient and meticulous work in astronomy was done not by men with telescopes, but by women with glass photographic plates and magnifying glasses. They were called computers, not the machines we know, but human beings doing the painstaking arithmetic of counting and measuring and cataloguing the light recorded on photographic plates. The pay was low. The credit, for a long time, was lower. But the work was extraordinary. Henrietta Leavitt was assigned to study a particular kind of variable star, a star that pulses in brightness, brightening and dimming over a regular, repeating cycle. These stars are called Cepheid variables after the first one studied, Delta Cepheid, which pulses on a schedule of about 5 1/3 days. And what Leavitt found somewhere between 1908 and 1912 was a relationship that would change our understanding of the universe's size and age more profoundly than almost any other single discovery in the history of astronomy. She found that the brighter a Cepheid star is, not how bright it appears, but how intrinsically bright it actually is, the longer its pulsation period. A Cepheid that takes 10 days to complete one brightening and dimming cycle is intrinsically more luminous than one that takes 5 days, reliably, predictably, without exception. This is what astronomers call the period luminosity relation, Leavitt's law. Do you see why this matters so much? If you know the period, so just by watching the star blink, you know the true brightness. And if you know the true brightness and you can measure the apparent brightness, the difference tells you the distance. The dimmer it appears compared to what it should be, the farther away it must be. The Cepheids were suddenly rulers, measuring sticks stretched across the cosmos. Every blinking Cepheid star in the sky became a distance marker, a milepost in the void. Leavitt's discovery made it possible for the first time to measure distances to objects far beyond what parallax could reach. Parallax works beautifully for nearby stars, the ones within a few thousand light years. But for objects farther away, the shift against the background becomes too small to measure reliably. The Cepheids extended the reach enormously. They could be seen in other galaxies, and once you could see them and measure their periods, you could know how far away those galaxies were. And it was with Cepheid distances that Edwin Hubble, in 1929, was able to show that the galaxies are moving away from us, and that the farther away a galaxy is, the faster it is receding. The more distant a galaxy, the greater its apparent speed. This regular relationship, distance times a constant equals speed, is what we call Hubble's law. But before we go further, there is a piece of this history that has been erased for too long, and which deserves to be said plainly. 2 years before Edwin Hubble published his 1929 paper, a Belgian priest and physicist named Georges Lemaître had already derived the same relationship, independently and theoretically, from Einstein's equations of general relativity. Lemaître calculated in 1927 that the universe should be expanding, and he estimated the rate from the available data. He published it first, and for decades the textbooks barely mentioned his name. Hubble, who had the telescopes and the photographic evidence, got all the credit. In 2018, the International Astronomical Union, the body that officially names and classifies things in the cosmos, formally recommended that the relationship be called the Hubble-Lemaître law. It was a correction long overdue. Georges Lemaître should have shared the credit from the beginning. He was, in the most literal sense, the man who first told us the universe was expanding. So, the expansion. What does it tell us about the age? The simplest way to think about it is exactly the film reversal I described a moment ago. If you know how fast the galaxies are flying apart, you can calculate, in principle, how long it would take them to have spread out to their current positions, starting from the moment everything was together. The inverse of the Hubble constant, 1 divided by h0, the number astronomers call Hubble time, gives you a rough estimate of that duration. For the current values of the Hubble constant, Hubble time works out to somewhere between 13.5 and 14 billion years, depending on exactly which value you use, which is already, you may notice, very close to the 13.8 billion years we are converging on. But the calculation is not quite that simple. Running a film backward assumes the film has been playing at the same speed the whole time, and the universe has not been expanding at a constant rate. Early on, in the first several billion years, gravity was the dominant force, and it was pulling everything back, slowing the expansion down. If the film slowed down as it ran forward, then you cannot simply reverse it at constant speed. The mathematics has to account for the deceleration. If it decelerated early on, then the universe needed more time to spread out to where it is now, so the age estimate goes up. And then something else happened. Something that nobody expected. About 5 to 6 billion years ago, roughly halfway through the universe's life so far, the expansion stopped decelerating and began to accelerate. The galaxies are not just flying apart, they are flying apart faster and faster. Whatever is causing this acceleration is something we do not fully understand. We call it dark energy, a name chosen essentially to say, we know it is real, we know it dominates the universe's energy budget at about 68%, and we do not know what it is. Dark energy is strange, but it is not a guess. The evidence for it came in 1998 when two separate teams of astronomers, one led by Saul Perlmutter, the other by Brian Schmidt and Adam Rees, were measuring the distances to a particular kind of extremely bright stellar explosion called a Type Ia supernova. And they found something that should not have been there. The supernova were dimmer than expected, not by a little, by enough that the teams had to sit with the result for a long time, checking every possible error before they felt confident enough to say it publicly. Dimmer meant farther than the models said they should be, which meant the universe had expanded more than expected in the time since those supernovae exploded, which meant the expansion was not slowing down as gravity would demand. It was speeding up. Something was pushing the universe apart, not just allowing it to drift. This was a genuinely disorienting discovery. There was nothing in the standard picture of cosmology to accommodate it. It required inserting into the equations an energy that fills all of space and has the peculiar property of pushing outward rather than pulling inward. A cosmological constant, similar to a term Einstein had once introduced and then removed from his equations, calling it his greatest blunder. It turned out that Einstein's blunder may have been removing it. Saul Perlmutter, Brian Schmidt, and Adam Rees shared the 2011 Nobel Prize in Physics for the discovery of the accelerating expansion of the universe. It is one of the most significant scientific findings of the past century. And for the age calculation, dark energy matters because it means the expansion history is not a simple decelerating curve, but a curve that first bends one way and then bends back the other. The mathematics has to account for this when working backward in time. When you feed all of this into the full lambda CDM model, lambda representing the cosmological constant that encodes dark energy, CDM standing for cold dark matter, and you run the calculation properly, the answer comes out to about 13.8 billion years. Now there is a complication here, a small but important tension in the numbers, and I want to mention it because leaving it out would be less honest than including it, and because the way astronomers are handling it is itself a kind of reassurance. The Hubble constant can be measured in two very different ways, using two completely different approaches. The first is what astronomers call the local method, or the distance ladder. You measure distances step by step, starting with nearby stars and working outward. Parallax for the nearest stars, Cepheids for nearby galaxies, and then using the Cepheids to calibrate Type Ia supernovae, those reliably bright stellar explosions, you can reach galaxies billions of light years away. The H0ES team, led by Adam Rees, has used this method to arrive at a Hubble constant of about 73 kilometers per second per megaparsec. A megaparsec is about 3.25 million light years. So what this says is, for every additional 3.25 million light years of distance, a galaxy is receding roughly 73 kilometers per second faster. It is a measure of how vigorously the universe is expanding right now, locally. The second method works from the other end of time. Instead of measuring expansion directly, it infers the Hubble constant from the cosmic microwave background, the oldest light in the universe, which we will come to properly in the next part of our journey. The Planck satellite, analyzing that ancient light, obtains a Hubble constant of about 67 kilometers per second per megaparsec, 67 versus 73. The two numbers disagree by about 9%, and the disagreement is not a small statistical wobble that might disappear with a bit more data. It is persistent. It has gotten more stubborn as measurements have improved on both sides, not less. The statistical significance of the tension, the confidence that it is not just a fluke, is somewhere around 4 to 5 sigma, which in the language of physics is the threshold beyond which scientists begin to take a discrepancy very seriously indeed. This is what astronomers call the Hubble tension. It is, as of the mid-2020s, one of the most discussed and most genuinely unresolved puzzles in modern cosmology. Some researchers think it reflects an unknown systematic error on one side or the other, some subtle mistake in the calibration of Cepheids or supernovae, or some subtle misinterpretation of the CMB data. Others think it might be pointing to new physics, some ingredient of the universe that the standard lambda CDM model is missing. There is no consensus yet. But here is the reassuring part, and it matters for our purposes, even with the tension. Even with the two values disagreeing by 9%. Even with the puzzle unresolved. Both values of the Hubble constant, when fed into the full cosmological model, give an age for the universe somewhere between roughly 13 and 14 billion years. The Planck value of 67 gives an age close to 13.8 billion. The SH0ES value of 73 gives an age somewhat lower, around 13.3 to 13.5 billion years. They disagree about the exact rate. They do not disagree about the order of magnitude. They do not disagree that the universe is approximately 14 billion years old, give or take half a billion years. The Hubble tension is a real and important puzzle, but it is not a puzzle about whether the universe is billions of years old. It is a puzzle about the last decimal place, and that is a very different kind of uncertainty. Science, at its best, is honest about what it doesn't fully know. The Hubble tension is the field being honest, saying here is a discrepancy, here are the two measurements, here is the gap, and we have not yet resolved it. That honesty is actually part of why the number 13.8 billion years is trustworthy. A field that acknowledges its uncertainties is a field that takes precision seriously. A field that glosses over discrepancies in order to present a tidy picture is a field you should be more cautious about. The Hubble tension is not a crack in the foundation. It is scientists doing exactly what they should, noting that two precise instruments are reading slightly differently and refusing to pretend otherwise while they work to understand why. So the expansion clock tells us, depending on exactly which measurement of the Hubble constant you trust, somewhere between 13 and 14 billion years, and that, you will notice, overlaps very neatly with what the stellar clocks told us. The oldest globular clusters somewhere around 12 to 13 billion years old. The Methuselah star, with its refined age somewhere around 13 to 14 billion years. The white dwarf embers cooling in the oldest clusters around 12 to 13 billion. The radioactive isotopes ticking down in ancient stars around 13 to 14 billion. Two completely unrelated kinds of physics, two completely unrelated measurement traditions, two different histories, two different instruments, two different chains of reasoning stretching back to two different moments in the development of modern science. And they are all pointing with their different fingers at the same stretch of the timeline. That is not a coincidence. That is what convergence looks like. And there is more convergence still to come from a third clock entirely, one that has nothing to do with stars or with the rate of expansion as we measure it today. A clock that reads the age of the universe from the faintest, oldest, most ancient light that exists. A glow so cold it barely qualifies as warmth at all. A whisper of heat left over from a time so early that there were not yet any stars, not yet any galaxies, not yet anything at all except a blinding, roaring, unimaginable density of energy and matter pressing outward in all directions. The third clock is the cosmic microwave background, and its story begins long before Arno Penzias and Robert Wilson accidentally found it in 1965. Though we will certainly get to the pigeons. But before we do, I want to let you rest here for a moment in what we have found so far, because it is something worth sitting with. The universe, as best as two of our three clocks can tell us, is somewhere around 13 to 14 billion years old. The stars say it. The expansion says it. Two independent roads built from entirely different materials leading to the same stretch of territory on the map of time. There is something calming about that, I think. Not because the numbers are precise to the last digit, they are not, and science knows they are not, but because they agree. Because independent methods built by different people at different times using different physics happen to converge. That convergence is the closest thing to certainty that science can offer about a question this ancient. It is not dogma, it is triangulation. And triangulation, when the lines cross, is how you know you are not lost. Wherever you are tonight, whatever lamp is still on, whatever quiet has settled into the room around you, the universe that contains you and your room and your lamp and every particle that makes them up is about 13.8 billion years old, not because someone declared it, because three separate clocks measuring three separate things came back with the same answer, and the agreement of those clocks is the evidence. We have met two of them now, the stars burning their slow hydrogen fires and cooling their embers and ticking their radioactive heartbeats. And the expansion, the vast outward drift of galaxies that run backward in time, collapses toward a single beginning. Both say about 13 billion. Both say it from entirely different directions. The third clock is the most ancient witness of all. It does not measure stars. It does not measure motion. It measures light itself. The oldest light in the universe, frozen into a pattern that encodes everything about the cosmos as it was less than 400,000 years after it began, long before the first star had ignited, long before there was anything to measure, just plasma and light and the deep hum of something enormous in the process of becoming. That light is still with us. A faint glow, cooled now almost to nothing, spreading through every corner of the cosmos, passing through this room, through the wall behind your head, through you. Warm, in the loosest possible sense, at 2.725 degrees above absolute zero. And that light, that ancient cold glow, carries within it the most precise measurement of the universe's age that we have ever managed to extract. Not from a single satellite or a single team, but from 3 generations of satellites, each one sharpening the picture a little more, each one listening more carefully to the oldest story in existence. That is where we are going next, to the cosmic microwave background, to the moment 380,000 years after the beginning, when the universe finally became transparent and light was set free to travel forever. To Arno Penzias and Robert Wilson and their inexplicable hiss and their very memorable pigeons, and to the way a pattern of almost imperceptible hot and cold spots scattered across the entire sky tells us with extraordinary precision just how long ago everything began. But not quite yet. Take a breath first. Let the stellar clock settle in if you haven't already drifted into something softer. The oldest stars, burning their quiet billions of years. The Methuselah star in Libra, carrying its ancient light across 190 light-years to eyes and telescopes patient enough to notice. The clusters, NGC 6397 and M92, wheeling slowly around the halo of our galaxy, older than the galaxy itself, was young. White dwarfs, fading like coals. Uranium and thorium, decaying with the patience of deep time. They are all out there right now. While you are here, wherever here is for you tonight, all of that is happening in the sky above you at this very moment. The old stars burning. The expansion carrying the galaxies apart at speeds you could not feel even if you stood in the void between them. And the ancient light, the microwave background, flowing through everything. You don't have to hold all of it at once. Let it sit around you loosely. We will come to the third clock in good time. So, the second clock, and this one works differently from the first. The stellar clock reads age from chemistry and physics written inside the stars themselves. The rate at which hydrogen fuses, the curve of a star's life, the cooling of its remnant. It is, in a sense, a clock built into matter. But the second clock reads something else entirely. It reads space itself, the fact that space is moving, the fact that the universe has been growing ever since the beginning, and that if you could run that growth backward, like rewinding a film, frame by patient frame, you could calculate the moment when everything was in the same place. The moment the film began. To do that, you need to be able to measure distances, enormous distances, distances so vast that light itself, the fastest thing in the universe, takes millions or billions of years to cross them. And that is not obvious, that is not easy. The story of how we learn to measure those distances is, in its own quiet way, one of the most beautiful stories in the history of science. And it starts not with Edwin Hubble, whose name you may already know, but with a woman whose name has been missing from most tellings for far too long. Her name was Henrietta Swan Leavitt. She worked at the Harvard College Observatory in the early years of the 20th century, at a time when the work of measuring and cataloguing stars was performed largely by women, called computers, because that is what they were, human beings who computed, who measured, who classified, for modest wages and with little institutional recognition. Leavitt was one of them. She had a gift for precision, for patience, for noticing things that other people had catalogued without quite seeing. What she was given to study was a class of stars called Cepheid variables. These are stars that pulsate. They brighten and dim on a regular cycle, like a slow heartbeat, some over a few days, some over many weeks. And what Leavitt noticed, working through a large set of these stars in a nearby companion galaxy called the Small Magellanic Cloud, was something remarkable. The slower the pulse, the brighter the star. Not just a loose trend, a tight, clean mathematical relationship. The period of the pulsation, how long each brighten and dim cycle takes, was directly and predictably linked to the star's true luminosity, its actual energy output. Leavitt published her initial findings in 1908 and extended them into a precise, calibrated law by 1912. Think about what that means for a moment. If you have a Cepheid variable star anywhere in the sky, anywhere in the universe within the range of your telescopes, you can measure its period simply by watching it, watching how quickly it brightens and dims. From that period, using Leavitt's law, you can calculate how bright it truly is, how much light it is actually pouring into space, and then you compare that true brightness to how bright it appears in your telescope. The difference between how bright it is and how bright it looks tells you exactly how far away it is. The fainter it looks relative to how bright it should be, the farther it is. It is like knowing a lighthouse bulb's wattage. If the lighthouse has a 10,000 watt bulb, and you know that, then how bright the light appears to you from where you are standing tells you precisely how far away the lighthouse is. Leavitt gave astronomers a lighthouse with a known wattage, and the lighthouse was built into the stars themselves. This single discovery, Leavitt's law, the period luminosity relation of Cepheid variable stars, made it possible to measure the universe. Without it, the expansion clock doesn't exist. Without it, the cosmic distance ladder has no second rung, and the whole structure comes down. She is the unsung foundation. She died in 1921 before the full consequences of her work had become clear. She was proposed for a Nobel Prize in 1924 by the Swedish mathematician Gösta Mittag Leffler, who did not know she had died. The prizes at that time were not awarded posthumously. So when we talk about measuring the size and age of the universe, we are standing, whether we acknowledge it or not, on Henrietta Swan Leavitt's careful work, on her patient measurements of pulsing stars in a nearby galaxy, on a law she wrote down in a logbook at Harvard before most of the universe beyond our own galaxy had even been confirmed to exist. Now, the distance ladder. Measuring cosmic distances is something astronomers do in stages. No single method reaches from here to the edge of the observable universe in one step. Instead, each method carries you to a certain distance, and at that distance you calibrate the next method, and that one carries you farther, and you calibrate the next. Each rung of a ladder, each one resting on the one below. The first rung, the one closest to home, is parallax. Hold up a finger in front of your face and close one eye, then the other. Watch your finger seem to jump against the background. That jump is parallax. The shift in apparent position caused by viewing the same object from two slightly different positions. Earth orbits the Sun, so in January we are on one side of the orbit and in July we are on the other side, nearly 300 million kilometers away. For nearby stars, that baseline is enough to measure a tiny positional shift against the more distant background of farther stars. From that shift, trigonometry gives the distance directly, no assumptions needed. This is the most reliable rung because it is pure geometry, but parallax fades out. Beyond a few thousand light-years, the shifts become too small to measure reliably, even with modern instruments. That is where Leavitt's Cepheids take over, the second rung. Find a Cepheid, time its pulse, read its true brightness, compare to its apparent brightness, calculate the distance. Cepheids push the ladder outward to tens of millions of light-years, deep into neighboring galaxies. And then there is a third rung, stretching the ladder to the edges of what we can see. Type Ia supernovae. A supernova is a stellar explosion. When a star reaches the end of its life in certain ways, it detonates with such force that for a brief time it can outshine the entire galaxy it lives in. Most supernovae come in many varieties and brightnesses, so they are not useful as standard measuring tools, but type Ia supernovae are special. They occur through a very specific mechanism, a white dwarf, one of those stellar remnants we met in the first clock, sitting in a binary system, slowly pulling material from a companion star onto itself. Matter accumulates on its surface. The white dwarf gets heavier, and there is a threshold. It is called the Chandrasekhar limit, named for the Indian-American astrophysicist Subrahmanyan Chandrasekhar, who calculated it in the 1930s. The limit is approximately 1.4 times the mass of the Sun. When the white dwarf accumulates enough mass to approach that critical threshold, it can no longer support itself. The entire star collapses inward almost instantaneously, and then the resulting nuclear reactions tear it apart in an explosion of staggering energy. Because every type Ia supernova reaches this same critical threshold, 1.4 solar masses, no more, no less. Every type Ia supernova explodes with nearly the same intrinsic brightness. A standardizable candle, not perfectly identical, but astronomers have refined the calibration carefully enough that they know exactly how bright each one truly is, and from that, how far away each one is. Type Ia supernovae are bright enough to be seen billions of light-years away. They extend the distance ladder to the very edge of the observable universe. And it was there, at those enormous distances in 1998, that something unexpected happened. Something that changed our understanding of the universe, and matters for our age calculation in a way that is worth sitting with for a moment. Two independent teams of astronomers were studying distant type Ia supernovae, expecting to measure how quickly the expansion of the universe was slowing down, because it seemed natural to assume that gravity, the mutual pull of all the matter in the universe on all the other matter, should have been breaking the expansion over the billions of years since the beginning. The question was just how much the breaking had occurred. What they found instead was that the distant supernovae were fainter than they should have been. Not brighter, fainter. Farther away than expected. Which meant The universe was not slowing down at all. It was speeding up. The expansion was accelerating. Something was pushing the universe apart faster and faster, overcoming gravity on the largest scales. That something is what we now call dark energy, a name that is honest about how little we understand it. It appears to be an energy inherent to space itself, present everywhere, causing the fabric of the universe to stretch at an ever-increasing rate. It makes up approximately 68% of the total energy content of the universe. We do not know what it is. We only know what it does. The three astronomers who led this discovery, Saul Perlmutter, Brian Schmidt, and Adam Rees, received the 2011 Nobel Prize in Physics for it. And dark energy matters for the age clock in this way. The expansion of the universe has not been constant. In the early universe, gravity was dominant and the expansion was slowing. Then, roughly 5 to 6 billion years ago, as the universe grew large enough that dark energy began to dominate over the diluting matter, the expansion started accelerating. The universe has been expanding at different rates at different times. This matters because the simplest way to use the expansion rate as a clock, the method called Hubble time, is to take the current expansion rate, invert it, and imagine everything running backward at that constant rate. That gives you a rough figure, somewhere between 13.5 and 14 billion years for modern measurements of the expansion rate. But the universe has not always been expanding at its current rate. Early on, it was slower than it is now, so running backward at today's rate alone would overshoot the true age slightly. The full calculation has to account for the entire history of the expansion, the early deceleration under gravity, and the more recent acceleration under dark energy. When you do the complete accounting using the standard lambda CDM model, the expansion clock lands right near 13.8 billion years. The correction isn't enormous. We're not talking about the answer changing by a factor of 2, but it is real, and the precision we are aiming for requires we handle it carefully. Now, the expansion itself and the man, or rather the men, and their complicated history, who measured it. In 1929, Edwin Hubble published a paper containing one of the most remarkable scatter plots in the history of science. It showed galaxies plotted by their distance on one axis and by how fast they were moving away from us on the other axis. The points were scattered messily the way early data always is, but through them ran a clear trend. The farther a galaxy, the faster it was receding. Not just moving away in a precise proportional way. Double the distance, double the recession speed. The universe was expanding, and the rate of that expansion could be expressed as a single number, a constant relating distance to recession velocity. That constant is now called the Hubble constant, denoted h0. But here is the part of the story that the textbooks have often omitted. 2 years before Hubble's 1929 paper, in 1927, a Belgian physicist and Catholic priest named Georges Lemaître published a paper in which he derived the expansion of the universe theoretically from Einstein's equations of general relativity, and estimated what the expansion rate might be from the observational data available at the time. Lemaître's paper appeared in a relatively obscure Belgian journal and was not widely read by the English-speaking scientific community. When it was eventually translated, the section containing his numerical estimate of the expansion rate was, mysteriously, omitted from the English version, something that has been a matter of historical discussion ever since. Lemaître was not just a bystander, he was, arguably, the first person to understand what an expanding universe implied. He followed his theoretical derivation to a remarkable conclusion. If the universe is expanding now, then running it backward in time should bring everything together to a single point of unimaginable density at a finite moment in the past. He called this the primeval atom, the seed from which everything grew. We call it the Big Bang, though Lemaître himself never used that phrase. In 2018, the International Astronomical Union formally voted to recommend calling it the Hubble-Lemaître law, in recognition of both men's contributions. The expansion of the universe has two parents, so when you hear Hubble's law in the future, you might carry with you a small, quiet note. Lemaître was there first with the theory, and Leavitt was there first with the measurement tool that made the distances possible at all. Now, the Hubble constant itself. And a very interesting problem. The Hubble constant is measured as a speed per distance. In the units cosmologists use, kilometers per second per megaparsec. A megaparsec is about 3.26 million light-years, so a Hubble constant of, say, 70 means that a galaxy 1 megaparsec away is receding at 70 kilometers per second. A galaxy 2 megaparsecs away is receding at 140 kilometers per second, and so on, scaling linearly with distance. The inverse of the Hubble constant, 1 divided by h0, is called the Hubble time, and it gives a rough approximation of the universe's age in the same way that knowing a car's average speed lets you estimate how long it's been driving if you know how far it's come. But what is the actual value of the Hubble constant? And this is where something interesting lives. A thread that is worth following gently without alarm, because what it shows us is something reassuring rather than troubling. There are currently two main ways to measure the Hubble constant, and they give slightly different answers. The first way is what astronomers call the distance ladder, the same ladder we just climbed, rung by rung, parallax, then Cepheids calibrated by Leavitt's law, then type Ia supernovae. This method measures the expansion directly, locally, using actual observations of real objects at known distances. The most precise version of this measurement is carried out by the Cepheid 0ES team, an acronym for supernova H0 for the equation of state, led by Adam Rees, the same Adam Rees who shared the 2011 Nobel Prize for the discovery of accelerating expansion. The SH0ES measurement of the Hubble constant, refined over many years and recently confirmed with exquisite precision by the James Webb Space Telescope's sharpened Cepheid measurements, comes out to approximately 73 kilometers per second per megaparsec. The second way is entirely different. Instead of measuring the expansion directly from local objects, it infers the Hubble constant from the cosmic microwave background, from the pattern of the oldest light in the universe. The Planck satellite's precise measurements of that ancient light, fitted to the lambda CDM model, give a Hubble constant of approximately 67 kilometers per second per megaparsec, 67 versus 73, a difference of about 9%. And the disagreement is not a matter of both measurements being imprecise. Both are highly precise, and the statistical significance of the discrepancy is real, somewhere around 4 to 5 sigma, which in the language of statistics means it is almost certainly not caused by random chance. The two measurements are each saying something slightly different about the universe. This disagreement is known as the Hubble tension, and it is currently one of the most actively discussed open problems in cosmology. Now, why am I telling you this? You are lying somewhere comfortable, the light is low, and you came here to feel settled and calm. And I am telling you about a disagreement that the smartest cosmologists in the world have not resolved. Here is why. Because the tension is actually a piece of the reassurance story, not a threat to it. Notice what the disagreement is about. It is not about whether the universe is 10 billion years old or 50 billion years old. It is not even about whether it is 13 billion or 14 billion years old. Both values, 67 and 73 kilometers per second per megaparsec, when fed into the full lambda CDM calculation accounting for dark energy and the complete expansion history, both give an age of the universe somewhere between roughly 13.5 and 14 billion years. The tension is about the precise rate of expansion, which shifts the age calculation by a relatively small amount within that range. The famous 13.8 billion years from the Planck satellites CMB measurement corresponds to the lower Hubble constant of 67. A calculation using 73 gives something a bit less, perhaps closer to 13.4 or 13.5 billion years. Both are near 13.5 to 14 billion. Both are consistent with the stellar flaw we met in the previous clock, which told us the universe is at least around 13 billion years old. None of these numbers put stars older than the universe. The tension is real, it is interesting, it may point to new physics we have not yet understood, but it does not threaten the broad convergence. All roads still lead to the same neighborhood. The fact that cosmologists are publicly, openly, actively troubled by a 9% discrepancy in a single constant, that they have spent years checking and rechecking their instruments, their calibration assumptions, their data pipelines, looking for errors, publishing their methods in exhaustive detail so others can find mistakes if they exist. That is not a sign of a field in crisis. That is a sign of a field that takes precision seriously enough to worry about 9%. That is what rigorous science looks like from the inside. It worries about the small things loudly and transparently because the small things matter, and it does not paper over the discrepancies with confident-sounding words. It publishes them, argues about them, and keeps measuring. That transparency is part of what makes the agreement of the three clocks meaningful. The people doing this work are not in the business of forcing numbers to match. Let the Hubble tension sit quietly in the background, then a real and interesting thread that the field is actively pulling. Not alarming. Not a reason to doubt 13.8. More like a gentle reminder that the universe is not done surprising us, even on questions we thought we had largely answered. The expansion clock, even with this open thread, arrives near 13.8 billion years, and it arrives there through a chain of reasoning that has nothing to do with the first clock. Leavitt did not study stellar evolutionary models. The main sequence turn-off method does not involve measuring recession velocities. The cosmic distance ladder is built from observations of pulsing stars and exploding white dwarfs, not from the nuclear physics inside a hydrogen-burning core. Clock 1 and Clock 2 are independent in their foundations, and yet they point to the same neighborhood. There is one more thing worth sitting with before we leave the expansion clock entirely. Think about what Hubble's law actually says in the most physical terms. Every galaxy we can see, every one of the hundreds of billions of galaxies scattered through the observable universe, is moving away from us. And not just moving away in a very specific way, so that the farther it is, the faster it recedes. This sounds at first like it might mean we are at the center of some great cosmic explosion, the way debris flies outward from a bomb. But that is not what is happening. What is expanding is space itself. The fabric of space, the geometry of the universe, is stretching. Galaxies are not moving through space the way a ball moves through air. They are being carried apart by the stretching of the space between them. Every point in the universe sees every other point receding because the distance between every pair of points is growing. There is no center to the expansion. If you were living in a galaxy a billion light years from here, you would see the same thing we see. Everything moving away from you, with the most distant things moving fastest. An analogy that captures this imperfectly but helpfully is a rubber sheet being stretched in all directions at once. Draw dots on the sheet, now stretch it. Every dot moves away from every other dot, and dots that were farther apart move apart faster because there is more rubber between them being stretched. No dot is the center. The stretching is in the sheet, not in the motion of any particular dot through the sheet. Now imagine running that stretching in reverse. Shrink the sheet. All the dots converge. Keep shrinking, and eventually all the dots are in the same place. the moment when they were all together. That is the beginning. And the rate at which they are currently spreading apart, if you know the full history of how that rate has changed over time, tells you how long they have been spreading. It tells you the age. That is the expansion clock. And the rate they are spreading apart, in our best measurements today, says the spreading has been happening for about 13.8 billion years, corrected for the fact that expansion was once decelerating under gravity and is now accelerating under dark energy, with the transition happening roughly 5 to 6 billion years ago.
Run the film backward. Everything comes together. About 13.8 billion years ago, everything was in the same place, and then it wasn't. But here is something to hold in the dark before we move on. This clock, like the stellar clock before it, is not a direct measurement. There was no stopwatch running at the beginning of the universe. No one pressed start.
Instead, we measure what is happening now, the current recession velocities of galaxies at measured distances, the history of that acceleration and deceleration written into the brightness of distant supernovae. And we fit a model to all of that, and the model tells us when the film began. The confidence comes not from the measurement being direct, but from the model being tested against independent data again and again, and from the result agreeing with clocks built from entirely different physics, which is, in the end, the point. Two clocks, two entirely different kinds of physics. Stars reading their age from within through nuclear reactions and the slow death of gravity's handiwork. Space reading its age from without through the motion of galaxies and the precision of a pulsing Cepheid that a quiet woman at Harvard catalogued 100 years ago. Two clocks, no collaboration between them, no shared calibration, no common assumption that would force them into agreement. And they agree, not precisely, not to the decimal, but well within each other's uncertainties, well within the range you would expect from two imperfect methods pointed at the same truth from different angles. The stellar flaw says the universe is at least around 13 billion years old. The expansion clock says it is between roughly 13.5 and 14 billion, depending on which measurement of the Hubble constant you use. The Planck CMB result, as we will get to shortly, says 13.787 billion, and that too is in this same neighborhood. All three roads lead to the same small valley. But before we get there, before we come to the third clock, the ancient light, the hiss that Penzias and Wilson blamed on pigeons, the moment when the universe first became transparent and let its oldest light run free, there is one more thread from the expansion story worth drawing out, because it brings the two clocks into a historical conversation that is, I think, one of the most reassuring chapters in this whole story. In the 1990s, before the full precision of modern CMB measurements existed, before the Planck satellite had been built and launched, before the dark energy discovery of 1998 had reshaped our understanding of the expansion's history, the clocks disagreed, not by a little. They disagreed in a way that was genuinely troubling. Some measurements of the Hubble constant in the early and mid-1990s came in at relatively high values suggesting a Hubble time of perhaps 9 to 10 billion years, not 13 or 14, 9 or 10, and the oldest stars, by then already estimated at around 12 to 13 billion years through globular cluster methods, were apparently older than the universe the expansion clock was measuring. Stars older than the universe. The universe's own contents older than the universe itself. It was a logical paradox, and it was called the age problem, or the age paradox. And at the time, it was not a minor footnote. It was a genuine crisis that led some cosmologists to question whether the standard cosmological model was seriously wrong. And then two things happened. First, the Hubble constant measurements were refined, and the high values came down somewhat as better calibrations were applied and systematic errors were corrected. The value settled closer to what we use today. But the more important resolution came in 1998 with those two teams of astronomers studying distant type Ia supernovae. The discovery of accelerating expansion, the discovery of dark energy. Because dark energy changes the calculation of how old the universe is for a given Hubble constant. If the universe's expansion has been accelerating recently, meaning it was once slower than it is now, then the universe is actually older than the simple Hubble time calculation would suggest. Dark energy buys the universe more time. The age paradox dissolved. When the discovery of dark energy was incorporated into the model, the expansion clock stretched to meet the stellar clock, and they overlapped comfortably near 13.8 billion years. Now, why does this matter to us tonight? Here in the quiet. Because the age paradox and its resolution are not just historical color, they are evidence for the convergence. Think about it this way. If the three clocks were agreeing because someone had engineered them to agree, because there was some common flaw or shared assumption that was forcing them into line, then the clocks should not have disagreed so visibly in the 1990s. They should have been neatly consistent all along, but they weren't. They genuinely disagreed when the data were less complete. And then, as the data improved, as independent refinements were applied to each clock separately, they converged. On their own, through their own internal developments, without anyone sitting down and forcing an agreement, the three methods found each other. That is what real convergence looks like. It is not engineered, it is discovered. And discovering it required passing through the discomfort of a genuine disagreement first. The scientists who worked through the 1990s age paradox did not paper over the contradiction. They published it. They worried about it openly. They pursued it seriously. And when dark energy resolved it, not because it was a convenient fix, but because the supernova data independently demanded something very like it, the relief was real and hard-won. This is a pattern you find over and over in the history of science at its best. The temporary disagreements are not signs of failure. They are signs that the measuring tools are precise enough to notice when something is wrong, and that the people using them are honest enough to say so. Precision creates visible tension. Honesty keeps the tension visible until it is resolved, and resolution, when it comes, earns a kind of confidence that a clean, frictionless agreement from the beginning never could. The third clock, the CMB clock, did not exist in its precise modern form during the 1990s age paradox. COBE had flown, we will get to COBE, and confirmed that the cosmic microwave background was real and had the right thermal character. But the acoustic peaks, the fine structure that encodes the universe's composition and age with such precision, had not yet been mapped in detail. UMAP would do that after 2001. Planck would refine it to its finest precision after 2009. But when those measurements came in, when WMAP in the early 2000s gave a first precise age of roughly 13.7 billion years, and Planck eventually settled on 13.787, those numbers were not calibrated against the stellar clock or against the expansion clock. The CMB measurement uses different physics, different instruments, a different chain of inference. It just agreed. Three roads meeting at the same corner. That is where we are going next, to that third road, to the oldest light in the universe, the faint, cold glow that fills all of space in every direction right now, even as you are lying wherever you are lying tonight. Even in this room, in this air, those ancient photons are passing through everything, including you, ghostly and patient, carrying their 13.8 billion-year-old message. To the story of how a strange hiss in a radio antenna, blamed first on the droppings of pigeons who had taken up residence inside it, turned out to be the afterglow of the beginning of everything. To recombination, the moment, 380,000 years after the Big Bang, when the cosmos cooled enough that the fog of plasma finally cleared and light, for the first time in the universe's existence, was free to travel. To the acoustic peaks in the power spectrum of the CMB, the frozen sound waves of the primordial cosmos, preserving in their pattern a complete recipe for the universe's composition, geometry, and history, and to the number that all of that together produces. But for now, let the second clock rest quietly alongside the first. Henrietta Swan Leavitt, working by lamplight over photographic plates of the small Magellanic Cloud, timing the pulse of variable stars with a patience that changed everything. Georges Lemaître, a Belgian priest doing mathematics in an age when the universe was thought to be static and eternal, writing down equations that said, no, it is growing, it has always been growing, and if you follow the growth backward, it leads to a beginning. Edwin Hubble's scatterplot, imperfect and illuminating. The Cepheid variables pulsing their Morse code of distance across millions of light years. The white dwarfs that cross a threshold of 1, 4 solar masses and ignite in a flash of standardized brilliance, becoming the longest rung of the distance ladder. The barely perceptible faintness of distant supernovae that turned out to mean the expansion was not slowing, but accelerating. Dark energy, the universe's most mysterious ingredient, stretching space faster and faster. All of this woven together, pointing to roughly 13.8 billion years, and waiting ahead of us, the third clock. The oldest light, the hiss in the antenna, the frozen sound waves, and the way a pattern of almost imperceptible temperature fluctuations, 1 part in 100,000, scattered across the entire sky in every direction, tells us with extraordinary precision not just how old the universe is, but what it is made of and how it will continue to grow. That is a remarkable thing to be able to read from ancient light. We will read it slowly. So, the third clock. The first two took us on a long, winding journey. We looked at stars, old ones, the oldest we know, dense swarms of them huddled together in globular clusters, their ages written in the point where the most massive among them begin to give out. We stood with Henrietta Swan Leavitt and watched her pulsing stars breathe their distances across the dark. We ran the expansion backward like rewinding a film, all those galaxies sliding home toward a single moment, and we arrived both ways at a figure hovering near 13 billion years, give or take. Depending on which measurement of the expansion rate you use, a small disagreement that science is honest about, and that we will return to before we sleep. But the third clock is different from both of those. It does not look at stars. It does not measure how fast galaxies are moving away from us. It listens, in a sense, to the universe itself, to the oldest light in existence, light that has been traveling since before there were stars, before there were galaxies, before there was anything we would recognize. It reads an imprint left behind when the cosmos was less than 400,000 years old. And it does all of this quietly, passively. That light is here in this room with you right now, if you care to think about it that way. It has been traveling for nearly 14 billion years, cooled to just a whisper above absolute zero, pressing gently against everything it touches. Let's begin at the beginning of this particular story, or as close to the beginning as we can get. Imagine, if you can, the universe roughly 200,000 or 300,000 years after it was born. This is not something any of us can easily picture, and that is fine. Even cosmologists do not picture it easily. But try to hold just the broad texture of it. The universe is hot, incredibly hot. Not hot the way a fire is hot, not hot the way the surface of the sun is hot, but hot in a way that makes those comparisons seem almost comic. Thousands of degrees everywhere, not in one place, everywhere. Because everywhere was everything. Space itself was filled with a dense, glowing, churning plasma, a soup of charged particles, protons and electrons not yet joined into atoms, moving far too energetically to combine. And light, photons, the particles of light, trying to travel but unable to get very far before being scattered by one of those free electrons. Knocked sideways, deflected, absorbed and re-emitted, knocked sideways again. The universe, in other words, was opaque, like a very thick fog, but made of charged particles and radiation rather than water droplets. If you could somehow have stood inside it, which you could not, and the thought experiment breaks down almost immediately, but stay with it, you would not have been able to see anything beyond a very short distance. Light could not travel freely. It was trapped. This went on for about 380,000 years. And then something changed. The universe cooled enough. As the cosmos expanded, it cooled. The same principle that makes a gas cool when it expands. Slowly, gradually, the temperature dropped. And when it reached roughly 3,000 Kelvin, 3,000 degrees above absolute zero, which is hot by any ordinary standard, but cool enough by the standards of the early universe, something remarkable happened. The electrons slowed down enough that protons could catch them. Protons and electrons combined into neutral hydrogen atoms for the first time. Cosmologists call this moment recombination, which is technically a slightly misleading name, since the electrons and protons had never been combined before. This was their first meeting as atoms, not a reunion. But the name has stuck, and the event it describes is one of the most significant transitions in the history of the universe, because when the electrons were absorbed into atoms, the fog cleared. Suddenly, and in cosmic terms, it was sudden, though it took perhaps 100,000 years to complete. The universe became transparent. Light that had been trapped, scattered, bouncing endlessly off free electrons was released. It streamed outward in all directions, freely for the first time. The universe went from opaque to clear, and that light has been traveling ever since. That is what the cosmic microwave background is, that freed light. The afterglow of the moment the universe first became transparent, now 13.8 billion years old, stretched and cooled by the expansion of space from visible and near-infrared wavelengths all the way down into the microwave part of the spectrum. It has lost most of its energy to the expansion. It has cooled from 3,000 Kelvin to just 2.725 Kelvin, 2.725 degrees above absolute zero. Almost nothing. The faintest possible whisper of warmth. It fills the entire sky equally, coming from every direction at once, because that moment of recombination happened everywhere simultaneously, not in one place, everywhere. The whole sphere of the observable universe at its outermost edge in time is radiating this ancient light inward from all directions. You are sitting or lying at the center of it. That light is passing through the walls of your room. Through you. It interacts so weakly with ordinary matter at these low energies that it passes through almost everything without stopping. Trillions of these ancient photons traverse your body every second, carrying information about the infant cosmos, and you feel nothing. That is a quieter kind of wonder than the kind that keeps you awake. Just a fact to carry gently into sleep. Now, the discovery of this light is one of the finest accidental discoveries in the history of science, and it involves pigeons. The year was 1964. Arno Penzias and Robert Wilson were engineers working at Bell Laboratories in New Jersey. Bell Labs, one of those remarkable institutions that seemed almost supernaturally productive in the mid-20th century, a place where serious science and practical engineering lived side by side. Penzias and Wilson were working with a large horn-shaped antenna originally built for satellite communications, now repurposed for radio astronomy. They were trying to make careful, precise measurements of radio signals from the Milky Way, and they kept hearing a hiss, a persistent, steady, uniform hiss in the antenna. It did not come from any particular direction. It did not fluctuate with the time of day or the time of year. It was simply there, always, from everywhere, at a consistent level. It was ruining their measurements, and they could not get rid of it. They checked the electronics, they checked the connections, they checked everything they could think of. And then they noticed that a pair of pigeons had taken up residence in the antenna and left behind what Penzias and Wilson, in their eventual scientific paper, carefully described as white dielectric material, which is to say, pigeon droppings. They cleaned it out, they removed the pigeons, they chased the pigeons away, the pigeons came back. They removed the pigeons again, more permanently this time, in a way the paper does not dwell on. They cleaned the antenna thoroughly. The hiss was still there. It was not the pigeons. Meanwhile, across New Jersey at Princeton University, a team led by physicist Robert Dicke, which included Jim Peebles, who would later win the Nobel Prize for theoretical work on physical cosmology, had been working on exactly this question. They had predicted, based on the theory of the hot Big Bang, that the early universe must have produced a background glow of radiation, and that this glow, stretched and cooled by the expansion of space, ought to be detectable today as microwave radiation at very low temperature. They were actually in the process of building an antenna to search for it. They never needed to. Penzias and Wilson had already found it by accident while trying to understand a hiss they had blamed on birds. The two groups connected, the significance was understood almost immediately, and Penzias and Wilson published their detection in 1965. In 1978, they shared the Nobel Prize in Physics for the discovery. Dicke and Peebles, who had predicted the signal and were the first to understand what Penzias and Wilson had found, did not share the Nobel. That particular story is one cosmology tends to tell with a small, wry note of acknowledgement. But the discovery itself, the confirmation that this ancient light exists, that the afterglow of the early universe is detectable today, was a turning point. Not just for cosmology, for the entire project of understanding what the universe is. Because once you know the light exists, you can study it, and what you find when you study it is extraordinary. Here is what the cosmic microwave background looks like if you could see it with your eyes, and which you cannot because your eyes do not detect microwaves, but imagine you had the right kind of vision. You would see a sky that was almost perfectly, uniformly lit. The same brightness in every direction, not a galaxy here and a dark void there, just a smooth, even glow covering everything, almost perfectly uniform, but not quite. There are tiny fluctuations, variations in temperature of about 1 part in 100,000. In a temperature of about 3,000 Kelvin at the time of emission, the fluctuations are a few hundredths of a degree. Mapped onto the whole sky, they appear as a pattern of slightly warmer and slightly cooler patches speckled across the celestial sphere, like an incredibly subtle mottling. You would need very sensitive instruments to see them at all. Early satellites did not have the resolution, but they were there. These fluctuations matter enormously. They are not noise, they are not measurement error, they are signal, and the most information-dense signal we have access to about the early universe. And what they represent is the history of sound, or something very much like sound. In the early universe, the hot plasma was not completely still. It had slight density variations, regions where matter was just a little more concentrated, just a little less concentrated. Gravity pulled on the denser regions, trying to compress them. But radiation pressure, the pressure of all that trapped light bouncing around inside the plasma, pushed back, trying to expand them. Compression and expansion, expansion and compression, like a sound wave moving through air. Acoustic oscillations, physicists call them, or baryon acoustic oscillations, since baryons is the technical word for ordinary matter, protons and neutrons. These pressure waves rippled through the primordial plasma for the entire duration of that opaque phase, nearly 400,000 years. And then recombination happened. The electrons were absorbed into atoms, the plasma froze. The sound waves stopped propagating. They were frozen in place, like a snapshot taken at the exact moment the music stopped. The temperature fluctuations we see in the cosmic microwave background are that snapshot. The pattern of warm and cool patches in the sky is a record of where the sound waves were at the moment the universe became transparent. Physicists call the pattern the power spectrum, and it has a characteristic shape, peaks and troughs, the acoustic peaks, each one corresponding to a different scale of oscillation. The first peak is the largest. It corresponds to the scale on which a sound wave compressed once and stopped. The second peak corresponds to a wave that compressed, expanded, and then compressed again, and so on. Each peak carries information. The positions and heights of these peaks, which we can measure with great precision using sensitive satellites, tell us about the composition of the universe, how much ordinary matter it contains, how much dark matter, how much dark energy, the curvature of space, the expansion rate at the time of last scattering, all of it encoded in the pattern. The cosmic microwave background is the universe's autobiography, written in light that has traveled for nearly 14 billion years to reach us. And one of the quantities we can read from it directly using a mathematical model of the early universe, the standard cosmological model, lambda CDM, named for the cosmological constant lambda, which represents dark energy, and CDM for cold dark matter, is the age of the universe. Reading the pattern tells us the universe is approximately 13.787 billion years old, with an uncertainty of about plus or minus 20 million years, roughly 0.1%, on a number nearly 14 billion years old. That is the third clock's answer. Now let me tell you how we got there, how the instruments were built and improved and refined until that number could be stated with that kind of confidence, because it did not arrive all at once. The first step came in 1989. NASA launched a satellite called COBE, the Cosmic Background Explorer. Its instruments confirmed something that had been suspected but not demonstrated, that the cosmic microwave background has an almost perfect blackbody spectrum. A blackbody spectrum is what you get from an object in perfect thermal equilibrium, radiating purely as a function of its temperature. The fact that the CMB has this shape to extraordinary precision confirms that the early universe really was a hot, dense thermal bath, the kind of bath that the Big Bang predicts. John Mather and George Smoot shared the 2006 Nobel Prize in Physics for this work, Mather for the spectrum measurement, Smoot for finding the fluctuations, those 1 in 100,000 temperature variations. COBE's resolution was limited. It could see the fluctuations existed, but it could not map them in fine detail. The acoustic peaks were not yet clearly resolved, but the foundation had been confirmed. The second step was WMAP, the Wilkinson Microwave Anisotropy Probe, launched in 2001 by NASA, named after David Wilkinson of Princeton, one of the original Dickey group who had been preparing to find the CMB back in 1965 and never quite got the credit. WMAP had much finer resolution than COBE. It could map the fluctuations across the whole sky in sufficient detail to see the acoustic peaks clearly. It ran for 9 years, releasing results in phases. By the time its mission was complete, WMAP had measured the age of the universe at approximately 13.77 billion years. About 13.8 billion. The acoustic peaks, the composition, the geometry, everything fit together into a coherent picture. The universe is flat, WMAP confirmed. The geometry of space, on large scales, is not curved like a sphere or saddle-shaped. It is flat like an infinite sheet. That flatness is important because it simplifies the age calculation and confirms that the energy content of the universe, ordinary matter, and dark energy together, adds up to exactly the critical density. The third step was Planck. The European Space Agency's Planck satellite, launched in 2009, was the most sensitive CMB experiment yet. It mapped the fluctuations across the entire sky at much finer angular resolution and with greater sensitivity than WMAP. It ran until 2013, then continued analysis. The final data release came in 2018. The Planck collaboration, a large international group of hundreds of researchers, analyzed the full data set and produced the most precise measurement of the universe's age and composition yet obtained from the CMB. 13.787 billion years. Plus or minus 20 million years, that is the number from the third clock. From the acoustic peaks frozen in the oldest light in existence. That is what the cosmic microwave background tells us. And now, the convergence. This is the heart of it. This is what the whole journey has been leading toward. You have 3 clocks, each built on different physics, each developed by different people in different contexts, using different instruments with different sources of uncertainty and different potential failure modes. They are not calibrated against each other. They do not assume each other's results. They start from entirely different places and use entirely different chains of reasoning. Clock 1 says, the oldest things we can find, globular clusters, the stars near their cores, white dwarfs in their final cooling, ancient radioactive atoms in the spectra of old stars, point to ages of roughly 12 to 13 billion years. The universe must be at least that old, probably a bit older, a flaw set by the things that live inside it. Clock 2 says, run the expansion of the universe backward, correct for the way dark energy has been accelerating it, account for the changing expansion rate over cosmic history, and you arrive at roughly 13.6 to 14 billion years, depending on which measurement of the Hubble constant you use. Clock 3 says, read the pattern of acoustic peaks in the cosmic microwave background, fit the full lambda CDM model to the data, and the age is 13.787 billion years. Uncertainty, 20 million. They agree. Not exactly, not to the last decimal place. Clocks never agree to the last decimal place. But they overlap. The flaw from the stars is just below 14 billion. The expansion backward is 13.6 to 14 billion. The CMB is 13.787. These are independent estimates from independent physics, landing within a few % of each other. This is what scientists mean when they say a result is robust. Not that one method has been done very carefully, not that one instrument is very precise, but that multiple, completely unrelated approaches, each with its own strengths and its own potential weaknesses, all point in the same direction. The probability that 3 independent methods would agree by coincidence, if the true answer were significantly different, is very small. There is no good reason for stellar nuclear physics and cosmological kinematics and primordial acoustic waves to produce the same number unless that number is close to correct. The convergence is the argument. The number 13.8 billion years is not trusted because someone said so. It is trusted because 3 separate pieces of the universe, interrogated separately, gave back the same answer. But here is where it gets even more interesting and, in a strange way, even more reassuring. The clocks did not always agree. Go back to the 1990s. The Hubble constant was a source of genuine, heated controversy. Not a polite disagreement over statistical significance, but a real scientific dispute with real stakes. Different groups measuring the same quantity were getting answers that differed by nearly a factor of 2. Some measuring a Hubble constant that suggested the universe was only 8 to 12 billion years old. Others getting values that suggested it was closer to 16 billion. The spread was enormous, and this created a crisis because the oldest stars, the globular clusters, the ancient stellar populations, were already fairly well constrained to be around 13 billion years old. If the universe were only 8 to 12 billion years old, it would be younger than the stars inside it. The things would be older than the thing that contained them. Like finding a wine bottle that predates the vineyard. Or, more precisely, like finding a grandmother older than time itself. It made no sense. It was called the age paradox, or sometimes the age crisis, and it was taken seriously. This was not a quirk to be explained away. It was a genuine contradiction at the heart of cosmology. The resolution came in 1998, and it came from the third clock's closest neighbor, the cosmic distance ladder, the Type Ia supernovae. Two teams, one led by Saul Perlmutter, one jointly led by Brian Schmidt and Adam Rees, were studying distant supernovae. Type Ia supernovae, those standard candles, the white dwarfs that ignite at the Chandrasekhar limit of about 1.4 solar masses and explode with a consistent peak brightness. By measuring how bright they appeared at great distances and comparing that to how bright they ought to be, you can measure distance. And by measuring distance alongside redshift, you can map out the expansion history of the universe over billions of years. What both teams found independently in 1998 was that the distant supernovae were fainter than expected. Farther away than expected, the universe's expansion had not been decelerating under gravity, as most expected. It had been accelerating. Something was pushing the expansion faster and faster. That something is what we call dark energy. A property of space itself, perhaps, or some field pervading the cosmos. With a negative pressure that counteracts gravity on the largest scales, it makes up roughly 68% of the total energy content of the universe. We do not understand what it is, but we know it is there, and we know how it behaves, and its presence changes the expansion history of the universe in a way that adds time to the age calculation. With dark energy included, the simple Hubble time estimate, which assumed a constant expansion rate, gets corrected. The universe expanded more slowly in its early phases under the influence of gravity, then began accelerating more recently. When you fold all of this in, the age comes out longer than the naive estimate, and it brings the age estimate from the expansion rate into agreement with the stellar flaw and the CMB. The 1990s age paradox was solved by the same discovery that created dark energy cosmology. And here is why this matters for the question of trust. The clocks were once in contradiction. They pointed to different numbers, and the scientific community did not paper over the contradiction or quietly ignore it. They worked on it. They measured more carefully. They found something genuinely new. The accelerating expansion, dark energy, that neither side of the contradiction had predicted, that resolved the tension when included. The clocks then came back into agreement from a better and more complete picture of the universe. That is not the story of a number that was chosen and defended. That is the story of a number that was contested, almost abandoned, and then recovered when the picture became clearer. Science at its most honest. The convergence we see now is not the result of people agreeing to agree. It is the result of people measuring, discovering, revising, and converging on something closer to the truth. There is one honest note left to add, the Hubble tension, which we touched on in the second clock and which is still unresolved. The tension between the local measurement of the expansion rate, roughly 73 kilometers per second per megaparsec, from the SH0ES team, led by Adam Rees, and the early universe inference from Planck, roughly 67 kilometers per second per megaparsec, a gap of about 8 to 10%, statistically significant at 4 to 5 sigma, which is a high bar in physics. Something is either slightly wrong in one of the measurements, or perhaps in the model used to connect them, or perhaps there is something genuinely new in the physics of the universe that we have not yet accounted for. This remains open. Science does not have a definitive answer as of now, and the disagreement matters because it means the second clock's answer depends somewhat on which Hubble constant you use, and the two values give slightly different ages. But here is the important thing: even with this tension, the range of ages implied is roughly 13 to 14 billion years. The Hubble tension does not threaten the convergence in the broad sense. Both the faster expansion and the slower expansion, run backward and corrected for dark energy, lead to an age consistent with the stellar flaw and broadly consistent with the CMB. The precise value of 13.787 billion, the one we take from the Planck measurement, might shift slightly if the Hubble tension is resolved by finding new physics. But it would not shift to 10 billion, it would not shift to 20 billion. The agreement of the three clocks at the level of a few percent is robust. The Hubble tension is a puzzle at the edges of precision, not a challenge to the main result. Science is honest about the places where it does not yet have the full answer. That honesty is not a weakness, it is a feature. The field is telling you carefully and openly, we know the age to within a few percent, and here is the specific place where our two most precise methods disagree, and we are working on it. That transparency is why the number can be trusted. If a result were fabricated or poorly constrained, or based on circular reasoning, you would not find it surrounded by careful, published, honest acknowledgement of its remaining uncertainty. Three clocks, one answer to within a few percent, built on unrelated physics developed by different people, refined over decades, tested against each other, once in contradiction, now in agreement. The number is 13.8 billion years, give or take 20 million, about a fifth of a percent. We have been walking through these clocks for a long time now. Let's rest in the vastness of it for a moment. Somewhere in the Milky Way there are stars that formed when the universe was less than 1 billion years old. We can identify some of them. They are very old, those stars. They have been burning for nearly as long as anything has existed, and they will outlast the Sun by an enormous margin, burning cooler and quieter for trillions of years to come. They do not know, if stars can know anything, how old they are. But their ages are written in their chemistry, in the point where their brother and sister stars begin to fail, in the slow decay of thorium and uranium in their outer layers. And then there is HD 140283, the Methuselah star, in Libra, which caused such a stir because it appeared for a while to be older than everything. It is not. Its error bars, when measured carefully with the Hubble Space Telescope in 2013, allowed an age of roughly 13.7 billion years, comfortably inside the life of the universe, close to its beginning but not before it. A reminder that our measurements have limits, that error bars are not failures but honest statements of what we know and do not know, and that the universe has not conspired to trick us. Henrietta Swan Leavitt, working at the Harvard College Observatory at the turn of the 20th century, measuring the brightness of thousands of stars on glass photographic plates, found the heartbeat in the Cepheid variables. She did not get to see her discovery become the foundation of the entire cosmic distance scale. She died in 1921. By the time Hubble used her method to measure the distance to the Andromeda Galaxy and settle the question of whether it was inside the Milky Way or vastly beyond it, Leavitt had been gone for years. Her name should be as familiar as Hubble's. It is not. But the method is hers. Georges Lemaître, the Belgian priest who derived the expanding universe in 1927 before anyone had the observations to confirm it, was doing something extraordinary. He was following the mathematics where it led, even when it led somewhere radical. The universe is not eternal, it is not static. It had a beginning. The equations said so. He trusted the equations. He was right. The International Astronomical Union formally recommended calling it the Hubble-Lemaître law in 2018, nearly a century after Lemaître wrote down the equations, and nearly 60 years after his death in 1966. Arno Penzias and Robert Wilson did not go looking for the afterglow of creation. They were looking for something much more modest, and the universe reached out and tapped them on the shoulder in the form of an unremovable hiss and said, "Look what I have left for you to find." They cleaned the antenna, they chased the pigeons, the universe waited patiently, and when they finally understood what they had found, it turned out to be the oldest light in existence. And the Planck satellite, spinning in space at the second Lagrange point, 1.5 million kilometers from Earth, mapping the ancient afterglow to exquisite precision, finding the acoustic peaks, the frozen sound waves of the primordial plasma, reading the recipe of the universe from fluctuations 1 part in 100,000, producing the number 13.787 billion years with an uncertainty of 20 million. All of this is one story. Not 3 separate stories about 3 separate clocks, one story. The stars and the expansion and the ancient light are all chapters of the same history. The history of a universe that was born, that expanded and cooled and lit up with stars, that continued expanding, that began accelerating, that left behind evidence of everything it has done in 1,000 different forms, and that we have been patiently, imperfectly, honestly learning to read. You are part of that story, not a spectator. You are made of the same matter that was forged in those early stars, scattered into space when they died, gathered into new stars and planets, and eventually into you. The carbon in your cells was nuclear ash from a stellar furnace. The iron in your blood was forged in a supernova. The hydrogen in the water in your body dates to the first 3 minutes after the Big Bang, before there were stars at all, when protons and neutrons combined into the first nuclei. You are not observing the history of the universe from outside. You are a part of it, late and local, looking back. The cosmic microwave background that passes through you right now, those ancient photons carrying information about the universe at 380,000 years old, they pass through something that was made by that same universe, in that same expansion, from that same matter. There is a strange circularity in it. The universe is taking its own measure through us. And the number it arrives at, 13.8 billion years, is not an assertion, not a guess, not a single confident claim resting on one method that might be wrong. It is a convergence. 3 independent voices speaking from 3 completely different domains of physics, saying the same thing within a few percent. Oldest stars, about 13 billion at minimum. Expansion, backward, about 13.6 to 14 billion. Ancient light, 13.787 billion, plus or minus 20 million years. They agree because it is true, or close to true, as close as we can measure with the instruments we have and the honesty we bring to acknowledging what we do not yet know. That is a remarkable thing to be able to say about a question like this. How old is everything? And the answer, derived from stellar nuclear physics and the mechanics of cosmic expansion and the thermodynamics of the early plasma, is about 13.8 billion years. We are quite confident, not certain. Confident in the careful way that science uses that word, with error bars and an open question at the edges, and a willingness to revise if the data demands it. But the 3 clocks agree, and they will probably continue to agree as our instruments improve, as new data comes in, as the Hubble tension is eventually resolved one way or another, because they are measuring the same universe. And the universe is consistent with itself. It is late, wherever you are. Perhaps you've been drifting in and out for a while, in and out of the globular clusters, in and out of the distance ladder, in and out of the ancient plasma clearing into transparency. That's fine. That's more than fine. The universe has been going about its business for nearly 14 billion years. It will still be going about its business tomorrow. None of this is going anywhere. I hope some of it settled into you gently. The idea that the oldest stars mark a flaw, that the universe must be at least as old as the things inside it, and those things are roughly 13 billion years old. The idea that running the expansion backward, like rewinding a film of all those receding galaxies, gives you about 13.8 billion years. The idea that the oldest light in existence, pressed gently against everything from every direction, including this room, tells the same story when you read the pattern of frozen sound waves in its temperature. 3 clocks. 3 unrelated kinds of physics. 1 answer. If you enjoyed this slow journey through deep time, if it was the right kind of company for a quiet night, a gentle like and a subscribe would mean a great deal. Small creators like me rely on your support to keep making these. I'm grateful for every person who listens, and more grateful still for those who've been here before. Thank you for that. And wherever you are listening from tonight, what time is it in your corner of the world? A cold night, a warm one, a city going quiet, or somewhere already still? I'd love to know. Come and tell me. The universe has been here for nearly 14 billion years. And tonight, somewhere in it, you were here too, listening to old light and older stars and the patient work of people trying to understand what everything is made of and how long it has been going. That's a good thing to carry into sleep. Good night, kiddo. Grandpa'll leave the porch light on.